this lecture, we're finally beginning the topic of atmospheric radiation. And to begin with, we're going to start off with some definitions. So we have three definitions that we need to have in order to move forward in the topic of atmospheric radiation. The first is flux, which in the Wallace and Hubbs textbook is denoted by the variable E. And the flux is the total amount of energy that is emitted from an object in joules per second. And recall that joules per second is a unit of watts. The second definition is radiance. And radiance is the amount of energy that is in a solid angle. So it's watts per steradian. And you can recall that steradians are the unit of solid angle. And so what we're looking at is in spherical coordinates, we are looking at the amount of radiation that is coming in from a certain sector of the sky. So in this case, we have this area denoted in blue as dA. So the radiance is the amount of radiation that is coming in from that specific solid angle. And in order to calculate this solid angle in units of steradians, we have to be able to calculate the area of this, and then the unit of solid angle, omega, is defined as the change in that area as the change in radius. So dA over r squared. So recall that the change in the linear distance along a longitude line is equal to the radius times the change in the zenith angle. So phi is our zenith angle, and that's the angle from, in this case, the North Pole essentially, between this and this over here. This is our zenith angle. And so the linear length on this axis is r d phi. And then on the azimuth, which is our theta, is our azimuth angle, which is looking this direction. The distance on that is actually r times the sine of the zenith angle times the change in the azimuth angle. And that makes sense, because as you get closer to the point of origin up here on the North Pole, the azimuth distance actually shrinks to 0. And so if you have a sine of the zenith angle of 0, then that's going to be 0, giving you a 0 distance. And by the time you get to the equator, then the sine of phi is going to be equal to 1, and you get your maximum distance of r d theta. So the solid angle is defined as the integral over this quantity dA over r squared. dA, this area, is just the length times the width, which is the r squared times the sine of phi d theta. You go ahead and substitute that in. The r squareds cancel, and you're left with the solid angle is essentially the integral of over all solid angles is equal to the double integral of sine of phi d theta, where you must integrate over the appropriate zenith angles and over the appropriate azimuth angle in order to get the total solid angle that we have here. So flux, total amount of energy emitted by an object. Radiance, the amount of energy that is coming in from a very specific solid angle. And then we have irradiance, which is, in the Wallace and Hubbs textbook, is denoted with the variable F, and that's watts per meter squared. And so up here, we essentially have a slab of atmosphere, if you want to think of it that way, or a slab of a surface that's 1 meter by 1 meter. And you can have radiation that's coming in from essentially any direction in this hemisphere. And the irradiance essentially sums up all of the radiation that is coming regardless of the angle. So it's very different than the radiance. So up here we have a zenith angle of 0, which the radiation is coming straight through the surface. Over here we have a zenith angle of 45, which is this angle subtended from the point that's orthogonal to the surface over to here. And then you have the zenith angle of 60 degrees, which is now in this angle right here. So what's the relationship between radiance and irradiance? So by definition, the irradiance is going to be equal to the integral of the radiance times the cosine of the zenith angle times the change in the solid angle. So where does this cosine of phi come from? Well, when you have a zenith angle of 0, the radiation is coming down and it's at its strongest. And as you move to larger and larger zenith angles, the amount of radiation is actually being spread out over that surface. So that if you were to shine a flashlight straight on the board, it would be very strong. And as I tilt that flashlight, that same amount of energy is going to get spread over a larger and larger surface, which is actually reducing the energy in terms of watts per meter squared. So that's a multiplier to take into account the weakening of the radiation with the zenith angle. But we know that d omega, the solid angle, is sine of phi d phi d theta. We can substitute that in, and then we're left with completing that double integral over the appropriate bounds. So we're doing a hemisphere. So we want to assume that the radiation is isotropic, which means that the radiation itself, the source strength doesn't matter depending upon where you're looking at in the sky. That assumption is not always correct, but for this problem we're going to assume that it is. We have isotropic radiation. We are going to essentially be integrating over a azimuth angle of 2 pi, so we're going to go all the way around. So we're going to start off at the zenith angle of 0 down to the horizon of pi over 2, and then we're going to integrate that over the entire 2 pi of the azimuth to get a hemispheric dome over this 1 meter by 1 meter slab. So the limits of integration, therefore, are on the azimuth angle are 0 to 2 pi, and on the zenith angle, you're going from 0 to pi over 2. So we have this integral over here. This integral here is trivial. It's just going to be 2 pi. And then we'll just do a simple u substitution. For this one over here, we'll let u equal sine of phi. Du is going to be cosine d phi. We'll go ahead and make that substitution. Integrate u du to get us u squared over 2. Put in our appropriate values. And so we'll end up with f is equal to 2 pi I times the sine squared of pi over 2 minus the sine squared of 0 divided by 2. Of course, the 2's cancel. And the sine of pi over 2 is 1, so 1 squared is 1. The sine of 0 is 0, so that turns out to just be 0. And so you're left with the relationship for isotropic radiation over an entire hemisphere. The relationship between the irradiance and the radiance is that the irradiance is equal to pi times the radiance.